But what is very important for an engineer is to conceive the 1D modeling, all the aspects that go to build the differential equation. But that is all is going to be very, very important for you if you are trying to model a system and then convert that back to your time domain using inverse Laplace transform. Because you remember, when we integrated the sine, you got tan inverse, and when you integrated cos, you got log functions. Now we are at a very, very interesting pit stop, and here you have got some seriously interesting stuff to be unveiled, because I am talking about inverse Laplace transform. That means it would be it would be in the disguise, that is it would be hiding, and you will have to unveil it in order to understand what is the equivalent time domain expression, because it would be in the frequency domain expression, that is in terms of S. That is, you are given Laplace transform of certain function, and you will have to find out what is the exact equivalent time domain expression for that particular Laplace transform. Why this is important? Now look at the components of the curriculum that we have pursued. It is very, very logical. What is the end goal of Laplace transform? And one of the major applications of the Laplace transform is to model a system, that is, I'm talking about 1D model using an ordinary differential equation, and then convert that into an algebraic expression. And once you convert that into an algebraic expression, you can play around with it. You can either build a control circuit. We have seen that in the introductory lectures. You can, in fact, check the stability of the system. And once you do all that, you can also convert that back to time domain, and then study the time domain response, which is a very, very important thing if you want to control the system. And in order to convert from frequency domain back to time domain, the tool that is going to be available for you is inverse Laplace transform. Even if you are seeking allegiance to MATLAB, Maple, it is all built in. But here you are going to do it manually to understand what is what. Of course, if you once you get into a professional life, you would be using either of the math softwares that the company would use, or maybe an in-house code. But what is very important for an engineer is to conceive the 1D modeling, all the aspects that go to build the differential equation. And then once you get the transfer function with all your initial conditions, or once you get the relationship between input and output for a system, interpret that particular expression in terms of S for stability and other incidental requirements. It could be interpretation of the role of 0, which appears in the numerator, the roots of S of the expression in the numerator, or it is the role of poles, which are nothing but the roots of the expression in the denominator. Please go back to introductory lectures and appreciate what exactly I mean by zeros and poles and how they contribute to the behavior of the system. But that is all is going to be very, very important for you if you are trying to model a system and then convert that back to your time domain using inverse Laplace transform. So the idea is very, very important. Now you started with the Laplace transform of various functions, including the periodic functions, the unit step functions. And once you found that you are good at Laplace transform, then the idea is all the 1D models, are the differential equations, can be converted into S domain. Okay, can be converted into S domain, that is frequency domain. And once you did that, and once you extract all possible information from the S domain expression, the next step is to convert this into a time domain time domain expression so that you appreciate the response of the system for a given input. Response of the system for a given input, time domain response. So let me write it as time domain response. And how do you do it? This is done using inverse Laplace transform. So this is very, very logical. So you understand how to convert the differential equation into Laplace transform, that is the S domain. And in order to do that, we have spent quite amount of learning, including periodic functions, unit step functions, all that. And once you are done with that, then convert that into time domain using inverse Laplace transform. And the primary goal of all this is to solve the ordinary differential equations, which is the crux of the application of Laplace transform. It can be system of differential equations, or it could be one differential equation. It depends, but here we are going to solve just one differential equation of a given system, especially the second order differential equation, which dominates most of the physics and engineering applications. So our first step is done. We are quite familiar with finding Laplace transform of various functions. Now our second step is going to incept. We are going to learn how to get the inverse Laplace transform. And once these two are done, then finally we go to solve the differential equations, the ordinary differential equations. So now what are the methods that you are going to learn under this discussion, that is inverse Laplace transform? One is by inspection. If you are experienced, if you have done quite a number of problems, that is finding the Laplace transform, as soon as you look at the expression, things become quite obvious for you. We will give you some examples. And in some cases, if you get, let us say, tan inverse S by A, or you get a log of S square plus 1 by S square plus 4, if you get such expressions, it is quite obvious that you have got them by integrating. Because you remember, when we integrated the sine, you got tan inverse, and when you integrated cos, you got log functions. So obviously, in order to get back to the time domain, you will have to undo whatever you did. And how do you do? The anti-integration process is differentiation, differentiate it. But while doing so, you will have to adhere to certain rules. And also, once you do that, or even without differentiation, also in some cases, it is possible to manipulate the expression. And one of the techniques that for your curriculum that is important is completing the square. Okay, completing the square becomes very, very important for you. And then we'll also use partial fractions, because a given fraction can be split into several fractions using partial fractions, a method that you have learnt in your +1, and that is going to be very, very useful. And finally, we will use the convolution theorem. And this, in fact, if I have to practically relate this theorem, it is actually the relationship between input and output by a transfer function. So in fact, we would tell you how to physically interpret this. And we will also give you one practical example without actually solving, if you know the particular response of a system. So how do you actually write the result even without going into the convolution theorem, but understanding the principle of convolution theorem. Okay, so that is going to be very interesting. And in the examination, if you get an opportunity, say for example, you have got a product of two Laplace transforms and you're not familiar with any of these methods, then you can directly go and solve using convolution theorem. All the skill demand as far as the last method is concerned is familiarity with integration. That's it. And remembering of a few formulae. So that is it. So let's start looking at things in greater detail. So these are the methods. So under each method, we will try and solve a few problems so that you are absolutely trained for solving such problems. Because the moment you look at it, you first check whether it can be done by inspection. Second, whether I can differentiate, or without differentiating, can I complete the square? Or could I go for partial fractions, or should I necessarily go for convolution theorem? And in examination, For certain Laplace transform, the examiner himself or herself would mention that it has to be done via convolution theorem. So it is left to you by what method you would like to unveil and then get a frequency domain expression back to time domain. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.